Thank you for your kind words, ghost of Sir Isaac Newton. I don't know. Somebody has something better than that, I'm sure of it. All right, Mark Plyer coming back at you guys today. I don't know who that is other than by name. Top of the morning to you. Fun thing, did you know that if you simply add a sentence, any statement you make with an upward inflection in your tone, all of a sudden it will sound undoubtedly like a question? Literally any statement that you make? All you have to do to make it a question is just add an upward inflection? Okay. So right now we are going to jump in and we get 1.9. Again, the same header as the first little part. So we're going to be talking not with upward inflections because I don't want everything to sound like a question. We get to talk about inverse functions. Inverse. And I'm going to make it even a definition. We're just going ham today. Inverse functions. All right. The second that I make that language and I bring up inverse, do you guys remember seeing them last year? You probably all look back on it super fondly because you may not have any idea what I'm talking about. In black, just kidding, in this bright red color, I'm just going to write some stuff down. If I asked you for the name of a famous Lakota chief, you probably don't know. So in geometry, I tell a lot of lies, which I tell you guys a lot of lies too, but we don't have to focus on that yet. I use this big legend where I'm from about Chief Sokotoa. And all of a sudden, maybe you remember what these are for. Sokotoa, what's it represent? Sines, cosines, and tangents. Now, other question, it's been a while since y'all have taken geometry. If we know that we can write the sine of x like this, and just so we can focus on stuff with my language, this is the sine function of, what do we call this thing that I'm taking it of? Argument. Okay, did you guys ever undo a sine function? So not with the cosine, that won't work. But you might have used this. Or you might have used this. Okay, good. We're not doing trig stuff today, I'm sorry. But we are going to expand on this idea. What did you prefer, arcsine or written this one? Okay. So there's a couple things that I like and don't like about it, but we'll knock it out. We're going to define an inverse function real quick. So this is going to get real formal, and then we'll have to go back and build our intuition. We're going to say the following, and it's going to be kind of a wordy definition. We're going to let f and g be two functions. Cool. Pretty common in mathematics that a definition will start like this. Let f, and I'm not going to call them f of x or anything, f and g be two functions such that, and I'm going to use st, I'm going to let you guys catch up because I want to show you a pretty handy notation. Just now, we had an example of inverses. On the example you did before we started the lesson, f of g of x, what did it spit out? It spit out x. And what about when we switched the order? What did it spit out? Okay, so we're going to say f and g be two functions such that f of g of x turns out is exactly equal to g of f of x, which is exactly equal to x, like we saw in the example a moment ago. If we have this defined, so that's just given. We are given two functions that do this. Then, f of x and g of x are inverses of each other. Okay. The notation here, I hate it. You guys went with the one that is more easy to write, and I get it, why you would like it. There's a difference between a superscript and an exponent. There's a reason that I don't like the arc sign when you draw it with that -1, and I even make a little change to it. When we say they're inverses of each other, This gives us a few different ways that we can write it down. If I'm going to use IE for an example of this, or in other words, they're inverses of one another, and we just have to work on the notation. For this, we can make several statements, and we're not going to write like all of them, but I know for a fact that f of x, could I say that it is the inverse of g? Right? We said that, right? They are inverses of each other, so f is the inverse of g. If we want to say that, we write it like this. Now, when people say cancel, I really don't hate it. I don't love it, but like I'm going to give you a hard time, but you're cool with it. This one is much more misleading. And the notation is just a poor choice, but it became convention, so we roll with it. You are never, ever, 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 ever going to read, I want to say getting back together, but we're never going to read g to negative 1. It is not g to the negative 1. Never, 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 never. Instead, when you see that negative 1 superscript, notice I didn't call it an exponent. When you see it written here, it tells you it's the what? The inverse. So two ways that you can word this statement here. I'm okay with reading this in two ways. G inverse of x, and this is a more common way that I will say it, G inverse. Or it's wordier, which is why I don't say this one, the inverse of g of x. These are the appropriate ways to say that's written on the board. Never, ever, ever say g to the negative 1. Hate it, don't like it, don't want it. G inverse, or the inverse of g. Which one feels more natural to you guys? The inverse of g of x? Okay, I will try my best. I'll probably just bounce between these two things right off the bat. Now, a couple things happen with this. We can say this statement, but there's more. Could I say that g of x is equal to the inverse of some other function? G of x, based on all this, must also be equal to whose inverse? The inverse of f of x, or f inverse of x. They go both directions. Okay, the notation is ugly. A little bit. Or a lot of it. I don't know, it's kind of subjective. There's even more crazy stuff that happens with this. And we're almost done with the definition. And then the good news is it's just a lot of practice with these. Okay. Beyond just this, which is a whole lot of information. If f of g and g of f both spit out x, they're inverses of one another. And then we get all of this stuff true. Beyond that, here's the last big connection. We're going to see this show up graphically momentarily. If I wanted to know the domain of f of x, the domain of f is exactly equal to the range of g. Alternatively, what do you think the domain of g is equal to? The range of f, I heard somebody whisper. Now, in my notes, I have this written like 30 different ways because we can change whether we call it g or f inverse and all that stuff. They're ugly. Notation-wise, though, this is like everything just all at once. Okay. This part feels okay, I would imagine, because we just did one of these where we got exactly that. This part, notationally speaking, feels okay or feels awful? Okay, so at least we'll get used to it. This part. Probably less okay for some. We will see where this happens. And we're just going to make a couple quick, easy things to talk about. Okay, this is all really formal definition. Now, to be as nice as possible, I'm going to make a little follow-up underneath of this. When we think of an inverse, it doesn't have to be crazy. All an inverse does is undo something. That's it. And you guys already have a good understanding because I use the language undo. How do you undo a divide by 5? You multiply by 5. That's the multiplicative inverse, and it gets you back to the identity. How do you undo a square root? You square it. How do you undo a square? you take the square root. You guys are already familiar with the idea of inverses. I just want to stress this. A function and its inverse undo each other. Now, if you don't recall from your like good old days of trigonometric ratios and stuff, you use an arc sine to get the argument out of a sine function. You use arc cosine to undo a cosine. You use tangent to undo an arc tangent, and it's just back and forth all throughout. Whew. Okay, so we're going to jump right in with an example, and then we're going to dig into the graphs and see if we can't make some nicer statements. A function and its inverse do what to each other? Undo each other. Now, I'm not going to write it, but when you're looking for that undo, when they undo each other, notice what happens. It's like f and its inverse. It's almost like they just fall out and it leaves just the x, right? Or g and its inverse, they fall out and it leaves just the x, which is exactly what we're saying happens. I like the idea of cancel here. It feels more natural to use cancel in this sense rather than dividing, because inverses do cancel each other out. All right, we're going to do a quick problem or two, and we'll just kind of base in how it goes. Example. I just want to know inverse. That really was a question, just so you know. All right. Two colors. I want f of x to be the function, lost my spot, found my spot, x plus 4. And I'm going to make it 2x plus 4 to make it a little crazier. Sorry. This time, I'm going to make g of x, slight difference. Let's say it's x minus 4, and then we divide it by 2. I want you to determine for me, and we're going to divvy up. No, I lied. Determine if they're inverses. That's it. To check this, it's hidden within our definition. I'm going to shove you in the right direction. If they're inverses, by definition, if you compose them together, both directions, what had they better spit out? F of g and g of f better spit out what? X. Verify and check if that happens here. Once you have an answer of some sort, check with me, and if you're good, I'll have you try B as well. All right. I'm going to work through, and I don't know why I'm paused, but f of g of x should spit out this, where notice all I do is I keep these parentheses here just in case I need them, right? So when I plug that in here, anything convenient happened. They gone. And then this part, if I've not been saying it, it could be misleading. When I say they divide out, there's another word that I'm okay with. They what? One is the other one that I'm okay with. Because oftentimes it may look like I'm just magically dropping the parentheses. I'm going to add one more step in here that feels probably unnecessary, but it might not. Inside these parentheses, I still have my x plus 4. And if you think about that oneing out or dividing out, that's really what happens, is they just replace with a 1. What I've been guilty, wrong color, what I've been guilty of doing over and over is never making sure that we hit on what's actually going on here. To take out those parentheses, what's the operation that should happen? You should distribute, right? So I typically just divide them out and say, let's get rid of the parentheses, because in my head, I don't need to mention this. Now, I'll tell you, that's probably not true in reality. I should mention this. I might not again now that I have, but this is how my parentheses magically disappear. When they divide out, it's just a 1. And then they gone. Is it x? That's a good sign. Does it guarantee to me that they're inverses yet? We've done f of g and it worked out. G of f had better do the same thing. Does it? Okay, so I'm just going to go real quick. G of f would be g of 2x plus 4. And I'll show you like my amount of work that I would normally show, which I probably do that like every time anyway. But let's check. This becomes something minus 4 over 2. And that's 2x plus 4. In this situation, the same thing is going to happen. And I just want to make sure that I'm not like misleading anybody. The parentheses are a good habit. You should include them because if it's a negative, you're going to be really clear that you need to use them. What is the number that I don't bother to write? Here. 1. So if I were to distribute it, I would just get rid of the parentheses and nothing else would change. When I'm doing math on the board, and always call me out, I'm just going to work under the assumption that I've done that and I can already see that nothing changes. What happens with this plus 4 and the minus 4 if the parentheses were gone? They zero out, and then 2x over 2, they divide out, and I'm left with just x. Was g of f equal to x? Was f of g equal to x? So because that happens, what do we conclude these guys are? Inverses. So I would indicate my answer in one of two ways, or there's actually like a bunch of ways. I'm going to say yes, they are inverses. And the easiest way without me having to write a big sentence is to say that g of x is equal to the inverse of what function? F. This is my shortest sentence. Now, it's weird, but you could write it out in words. F and g are inverses. You could also say that f of x, alternatively, is equal to what? G inverse of x. Like, these are the same statement both times without having to write a bunch of sentences. Huggins.
Where did I'm late on this, but where did in the first one, 2x, why does that just become 2?
Right here?
Yeah.
So I'm plugging into 2x plus 4, and then here's my x that I'm replacing it with.
Never mind.
Yep, no, good question. Okay, on B, h of k, or k of h. Which one did you guys do first? H of k? That's natural. Let's check this out. H of k of x. I'm just going to plug it in right off the bat. K of x is this lovely thing, 2x minus 4. Does it feel different as you started working this one? Or if you haven't started working it, maybe it doesn't. Sean, I think it should feel different, but that depends on what we think different means. Let's just try this out. If I plug this in, h of k of x, that means anywhere in h that there is an x, I'm plugging that in. So let's just see what that does. Equals 3 times, there's my x as a variable, plus 1, and it's squared. And I'll just plug in my 2x minus 4. I'm just trying it out right now. Okay, first thought. Do you guys love doing more than you have to? No. I don't know how comfortable everybody in here is, and maybe differing levels, about multiplying and distributing and doing all that stuff in your head. Probably not everybody's super comfortable with it. That's totally fine. Can you tell me, without doing anything super crazy, are you going to get a bigger power of x to show up when you square this? If you just do the first, you're already going to get a 4x squared, right? Is there anything out here that's going to cancel off that x squared? So is it going to be just x that's left over? I guarantee it won't be, because I'm going to get a 4x squared and it's going to double. Like, it's just, there's no possibility of it. At this point, I know that this is not equal to x. And if you're just dying to see, like, not dying to see, if you want to see that thought process that I had, I did this. 3 times 4x squared minus 16x plus 16 plus 1. And I can already look at that and go, not a chance that thing's going to be just x. The fact that it's not x tells me what about these two functions? They are not inverses. If you get one to be x, you have to do the other to verify that it works both directions, because sometimes it will only do, like, f of g could be x, but the other one won't. If the first one doesn't work, you're done. Stop there. Not inverses. Okay. Now, there are all sorts of things that we can look at with this, and I want to make sure that, one, we can do it concisely in our notes, because that's always going to be nice if everything is nice and summarized. When I do stuff on Desmos, I don't care if you can use Desmos as much. Do you always understand everything I'm saying about the graphs? If not, what are you going to do? So we're going to ask. So check this out. I'm going to make a function real quick, and we're going to make a function for which we're going to be able to find the inverse super easily. So we'll do this. And let's see here. I think that I want to do the following. I want to have x cubed. So there it is. It's awesome. It does its thing. Can you guys tell me what undoes a cube? Not a square root. So I don't know how to type it in here, but I'm going to use exponents. This is the cube root, just so you know. X to the 1/3. And I'm going to graph them. Do these two graphs look similar to you? Kind of. If I throw this line in, does it look maybe more than just similar, but it looks like a reflection? Okay, here's the big part that I want us to look at. If I want to know f of 2, can you guys tell me what f of 2 is before I type it in? Here's f. If I plug in a 2, what's it make? So I know that the point 2, 8 is on the graph of f. If I plug in an 8 here, what's the cube root of 8? So check this out. I know that f of 2 is equal to 8, and this is the inverse. If I take g of 8, it spits out 2. We have a big connection here, and it's already been highlighted in the definition where we talk about the domain and range stuff. These pairs just seem to swap places or flip-flop between these functions. So we're going to go back here. Don't know what's going on with that, so we're just going to cancel somewhere. I don't know what's going on. We're going to look back at our notes, and we're going to make a big statement here. Okay. So important that it gets its own section, but it's going to be super short. We're going to talk about how does one think about graphing f inverse of x, or the inverse of f of x, if you'd rather. Okay. Several different things that we can knock out here. Turns out, though, the basic idea, if you can switch x and y around, you're going to get this easy, easy, easy. If f of a is equal to b for some function x. Now, in red, I'm going to put this here. This means that what ordered pair is on the graph? A, B is on the graph of f. And this is only if you need it. Okay, if you wanted to graph the inverse, maybe it's a huge pain to actually find the function, but I know that if f of a equals b, which is all this red information, then, nope, and we'll go back to black, then what do you think happens if I do f inverse of b? We just switch directions. Say it again. It equals a. Now, in the black is the most simple way you could put this. If f of a equals b, then f inverse of b equals a. But what that really means is if ab is on the graph of f of x, then the ordered pair ba is on the graph of f inverse. It means that without knowing a function, we could get, if I just give you f and say graph its inverse, you don't have to find it. You just have to be able to take infinitely many ordered pairs and do this. In essence, though, this gets even easier. To do this, to do this, simply reflect over y equals x. Now, I'm not going to give you homework tonight, just so you're aware, but I do want you to try this for me real quick. I'm going to give us a function that we don't know, like no idea what it is. So let's graph really sloppily. You don't even have to do it exactly like I do, but I want to try to at least be not too crazy. I'm going to graph this function. I'm going to call that f of x. Now, I'm assuming that I'm working with a square coordinate system, which means one dash is 1 in the x and the y direction, same scales on both of them. Could you graph me the inverse of this function without ever knowing what it is? So I'm going to rephrase that because maybe that's a big ask. I know that every ordered pair just switch places, right? Or, if you would rather, I know that it's simply like a reflection in what line? So check this out. I'm going to make this green line y equals x, and because I'm using a nice rectangular or square grid, it's just going to be perfect like that. If we draw this line, do you think you can reflect over it and at least roughly sketch the second graph? Okay, your challenge this evening is to do that. This is your homework. In the next 20 seconds, reflect and try to draw a different graph that's just like the reflection of this. If you feel like you're looking at DNA, that makes sense.
Could you go back to the example with B? I just never got it.
Yeah. Okay, I don't care if you have my exact graph. I'll come look at your graphs in a moment. Or at the start of class tomorrow. All right, what's lunch today? Cheeseburgers. Cool. Later, Raiders.